Hi, Stu Schwartz here from MasterMathMentor.com. This is video BC04 and the topic is improper integrals. It covers the BC manual pages 20 through 22. Suppose you are traveling along a road with a very slight decline. You are traveling at 100 feet per second, which is approximately 68 miles per hour. You take your foot off the accelerator and you find that your velocity follows the curve v of t equals 100 e to the negative 0.1 t. We are interested in what happens as time approaches infinity, meaning we are interested in the limit as t approaches infinity of 100 e to the negative 0.1 t, which is the limit as t approaches infinity of 100 over e to the 0.1 t, which is equal to 0. Now consider the total distance that you travel. We know this to be the area under the curve, which is shown in the figure. The question is, would the distance that you travel approach a limiting value, or would it increase without bound? You always have a positive velocity. So wouldn't you always get further and further down the road, which means that you would have a limitless distance? That's the question we need to answer. We now introduce the concept of an improper integral. That is a definite integral where one or both of the limits are infinite. It can be expressed as the integral from a to infinity of f of x dx, which can be interpreted as the limit as b approaches infinity of the integral from a to b of f of x dx. Or it can be expressed as the integral from negative infinity to b of f of x dx, which can be expressed as the limit as a approaches negative infinity of the integral from a to b of f of x dx. Or occasionally it can be written as the integral from negative infinity to infinity of f of x dx, which can be interpreted as the limit as a approaches negative infinity and b approaches infinity of the integral from a to b of f of x dx. The results of taking an improper integral are one of two possibilities. First, the integral may be divergent. This means that the limit is infinite. The interpretation is that the area under the curve is getting larger and larger without bound. Or the improper integral can be convergent, meaning that the limit is finite. The interpretation is that the area under the curve is also getting larger and larger, but will never exceed this limit. This cannot happen unless the limit of f of x as x approaches plus or minus infinity is equal to 0. Suppose b is some time greater than 0. The graph now shows the area under the curve from 0 to b, which represents the distance that the car travels in b seconds. And this distance can now be written as the integral from 0 to b of 100 e to the negative 0.1 t dt. We can integrate this expression, getting negative 1000 e to the negative 0.1 t, evaluated from 0 to b. And this turns out to be 1000 minus 1000 over e to the 0.1 b. So plugging in when b is equal to 10 seconds, the distance is 632.1 feet. Now when b approaches infinity, we are interested in the expression 1000 minus 1000 over e to the 0.1b. As b gets larger and larger, 1,000 over e to the 0.1b approaches 0, and therefore the answer is 1,000 feet. So this is a convergent integral, and the total distance that the car travels will be 1,000 feet. It will never get beyond 1,000 feet from its starting position. In problem 1, we're interested in the time lag between the car traveling 950 feet and 999 feet. Since we have an expression that represents the distance that the car travels, 1,000 minus 1,000 e to the negative 0.1b, we first set that equal to 950. We end up getting 50 equals 1,000 e to the negative 0.1b, and e to the 0.1b is equal to 20. Taking the natural log of both sides, we end up getting b is the natural log of 20 over 0.1, which is 29.957 seconds. So it takes almost 30 seconds for the car to travel 950 feet. We do the same thing for 999 feet, setting the expression 999 equal to 1,000 minus 1,000 e to the negative 0.1b. And from that, we get e to the 0.1b is equal to 1,000, and b is equal to the natural log of 1,000 over 0.1, getting 69.078 seconds. So the time lag is simply the difference between the two, and it takes 39.121 seconds to go from 950 feet to 999 feet. Now let's change the velocity slightly. We change it to v of t equals 400 over t plus 4. As we see in the graph, it is remarkably similar in shape to the original graph, and the area under the curve is shown from 0 to b. The distance, therefore, is the integral from 0 to b of 400 over t plus 4 dt. And that integrates to 400 natural log absolute value of t plus 4 evaluated from 0 to b, which is 400 natural log of b plus 4 minus 400 natural log of 4. So the total distance traveled is the limit as b approaches infinity of that expression, which turns out to be infinity, making this a divergent integral. That means that the car travels infinitely far from the time it starts to slow if you waited long enough. In number 2, you are asked to graph f of x equals x squared e to the negative x. The graph is shown to the right in green. It starts at 0, goes up quickly and peaks approximately at x is equal to 2, and then comes down, becoming asymptotic to the x-axis. In 2a, we're asked whether the integral from 0 to infinity of f of x dx could converge. In order to answer that, we take a look at the limit of f of x as x approaches infinity, and we find it's equal to 0. This means that when we are taking the accumulated area as x gets larger and larger, the area is getting larger and larger, but by smaller and smaller amounts. So since this limit is equal to 0, the integral from 0 to infinity of f of x could converge. It does not mean that it does converge. More work is necessary. In 2b, we're asked to find the integral from 0 to b of x squared e to the negative x dx. To perform this integration, we will use integration by parts, particularly the tabular method, which is shown on the right. This gives the quantity negative x squared minus 2x minus 2 times e to the negative x, evaluated from 0 to b. And that gives us negative b squared minus 2b minus 2 all over e to the b plus 2. In C, we're interested in the limit as b approaches infinity of the integral from 0 to b of x squared e to the negative x dx. We have already calculated the integral, so we're looking at the limit as b approaches infinity of the expression negative b squared minus 2b minus 2 all over e to the b plus 2. We can do this by L'Hopital's rule, and without showing the work, it's obvious that the denominator will always be e to the b, but the numerator will eventually become 0. So our limit is 2. This means that the area under this curve is 2, and the integral is convergent. In number 3, you're asked to graph f of x equals x plus 1 over 2x. The graph is shown to the right in purple. The graph is asymptotic to the right of the y-axis, comes down quickly, and becomes asymptotic to the line y is equal to 1/2. In 3a, you're asked whether the improper integral from 1 to infinity of x plus 1 over 2x dx could converge. Since this curve is asymptotic to the line y equals 1/2, the limit as x approaches infinity of f of x equals 1/2, which is not 0. So therefore the integral from 1 to infinity of f of x dx must diverge. If you think about it, it makes sense because the area is getting bigger and bigger and bigger without bound. In 3b, we're asked to show that formally. So we will be looking at the integral from 1 to infinity of x plus 1 over 2x. The best way of determining this integral is to factor out the 1/2 and look at 1/2 the integral from 1 to infinity of 1 plus 1 over x dx. And this turns out to be 1/2 times x plus natural log of x evaluated from 1 to infinity, which is infinity. Notice that we are now skipping the clunky notation with limit as b approaches infinity and just using the improper integral with infinity in it. In problems 4 through 7, we're asked to find the value of some improper integrals. Number 4 reads the integral from 0 to infinity of e to the negative x dx, which is negative e to the negative x evaluated from 0 to infinity, which is negative e to the negative infinity plus e to the 0, becoming 1 over e to the infinity plus 1, which is 1. We take some liberties, as mentioned before, with notation. There is really no such thing as e to the infinity. It really should be stated as a limit. However, it is easier to write it in this form. 5 reads the integral from 1 to infinity of 1 over x squared dx. We can write that as the integral from 1 to infinity of x to the negative 2 dx, which is negative x to the negative 1 evaluated from 1 to infinity, or negative 1 over x evaluated from 1 to infinity. At infinity, we get negative 1 over infinity, which is 0, minus at 1 we get negative 1. So our area is 1. Number 6 is the integral from negative infinity to infinity of 1 over x squared plus 1 dx. This is the first time we've had infinities at both limits. But the method is still the same. The integral of 1 over x squared plus 1 dx is the inverse tangent of x evaluated from negative infinity to infinity. This is equal to the inverse tangent of infinity minus the inverse tangent of negative infinity. The inverse tangent of infinity is simply pi over 2, minus the inverse tangent of negative infinity is negative pi over 2. So the area under that curve from negative infinity to infinity is simply pi. Finally, we have the integral from 1 to infinity of 1 over x cubed dx. This can be written as the integral from 1 to infinity of x to the negative 3 dx, and that as integrated turns out to be negative 1 over 2x squared evaluated from 1 to infinity. At infinity, our value is 0, and at 1, our value is negative 1/2. So 0 minus negative 1/2 is 0 plus 1/2, and the area is 1/2. Improper integrals are easily detected because their limits are either positive infinity, negative infinity, or both. But there is a second improper integral form that we must know, and that is the integral from a to b of f of x dx, where f is discontinuous at either a or b or both. In 8a, we're given the function f of x equals 1 over x, and asked to find the area bounded by the x-axis, the y-axis, the curve, and the line x is equal to 1. The graph is shown. Therefore, the area is equal to integral from 0 to 1 of 1 over x dx. This is an improper integral because 1 over x is not defined at x is equal to 0. But our method is still the same. We integrate and get the natural log of the absolute value of x between 0 and 1. That becomes natural log of 1 minus the natural log of 0. The natural log of 1 is 0, but the natural log of 0 does not exist. So therefore, the integral is divergent. This area gets infinitely large. There is a third and even more subtle improper integral form. It's the integral from a to b of f of x dx, where there exists a c on the closed interval a through b, where f of x is discontinuous. When we have that case, the integral from a to b of f of x dx is the limit as k approaches c from the left of the integral from a to k of f of x dx plus the limit as k approaches c from the right of k to b of f of x dx. We will see that in this next problem. Problem 8b is a little trickier. We have the same curve, y equals 1 over x, but we want to find the area bounded by the curve and the lines x is equal to negative 1 and x is equal to 1. So the area is simply the integral from negative 1 to 1 of 1 over x dx. But since 1 over x is discontinuous at x is equal to 0, we must write that the integral from negative 1 to 1 of 1 over x dx as the integral from negative 1 to 0 from the left of 1 over x dx plus the integral of 1 over x dx from 0 to the right to 1. When we evaluate these, we still get the natural log of the absolute value of x. And first, it's taken from negative 1 to 0, and then added the same expression, but from 0 to 1. This becomes the natural log of 0 minus the natural log of 1 plus the natural log of 1 minus the natural log of 0, which is infinity minus infinity. And since infinity does not exist, the answer is divergent. This problem raises some interesting mathematical ideas, and you might actually disagree with my conclusion. For instance, if you stated that the area is equal to negative 1 to 1 of 1 over x dx, forgetting about the discontinuity at x is equal to 0, you would come to the conclusion that the area is the natural log of the absolute value of x, evaluated from negative 1 to 1. This becomes natural log of 1 minus the natural log of 1, which is equal to 0. And you would come to the conclusion that the integral is convergent. And you very well may think it is, because it looks like we have an area to the right of the y-axis which is positive, and the same area to the left of the y-axis, and that is negative. So it looks like they should cancel out and the answer should be 0. But the answer is still that it is divergent and the area does not exist. And in 8b, we ended up with an expression infinity minus infinity. You might conclude that infinity minus infinity is equal to 0. 8 minus 8 is equal to 0. X minus x is equal to 0. Why not infinity minus infinity? But infinity is not a real number and does not behave according to the rules that you learn throughout algebra. So infinity minus infinity does not exist. Later in the course, we will learn to work with infinity and see some of the surprises that it can create. Redoing number 9, the integral of 1 to infinity of 1 over x cubed dx, we find that this was convergent to 1/2. However, in number 10, the integral from 1 to infinity of 1 over the cube root of x dx, this becomes the integral of x to the negative 1/3 dx, evaluated from 1 to infinity, which is 3x to the 2/3 over 2, evaluated from 1 to infinity. And this gives infinity minus 3/2, which is infinity, meaning that this is divergent. So in numbers 9 and 10, we had two problems, both in the same exact format, but 9 was convergent and 10 was divergent. So number 11 asks the values of n for which the integral from 1 to infinity of 1 over x to the n dx is convergent. In order to do this, we integrate the expression 1 to infinity of x to the negative n dx, and we get x to the 1 minus n over 1 minus n, evaluated from 1 to infinity. When we plug in infinity and 1, we find that this will converge to infinity to the 1 minus n over 1 minus n, minus 1 to the 1 minus n over 1 minus n. And in the last fraction, 1 to any power is 1. So this simply becomes infinity to the 1 minus n over 1 minus n, minus 1 over 1 minus n. Now, only if n is greater than 1 will the infinity to the 1 minus n become infinity in the denominator. And when that happens, the first fraction is 0. So if n is greater than 1, we get 0 minus 1 over 1 minus n. And for any value of n, this will converge. So the answer is this integral will only converge if n is a number greater than 1. Number 12 gives a graph of y squared is equal to 4 over x times the quantity x plus 1 squared. And we would like to find the area of the shaded region. In order to do this, we're going to solve for y, and we end up with y is equal to 2 over the square root of x times the quantity x plus 1. We need to integrate this expression from 0 to infinity. And that will give us the area of the top piece. So since the curve is symmetric to the x-axis, we can double it. In order to take this integral, we will let u equal to the square root of x, and therefore du is equal to 1 over 2 root x. Since we're going to put everything in terms of u, we will change the limits. So if x equals 0, u is equal to 0. If x is equal to infinity, u is also equal to infinity. The integration is clever. First of all, we will multiply the 2 times 2 and get 4. We also need a 2 in the denominator to get our du, so we will multiply also by 2 in the numerator. And we end up getting 4 times 2 integral from 0 to infinity of dx over 2 square root of x times the quantity x plus 1. X plus 1 is simply u squared plus 1. And we have the du, dx over 2 square root of x is du. So this complicated looking integral simply becomes 8, the integral from 0 to infinity of 1 over u squared plus 1 du. And you should recognize that integral as the inverse tangent of u. So the area will equal 8 inverse tangent of u evaluated from 0 to infinity, which is 8 inverse tangent of infinity minus 8 inverse tangent of 0. And the inverse tangent of infinity is pi over 2. So our answer is 4 pi.